Hello everyone, welcome to our last tutorial. So in this tutorial we are going to solve problems from problem set number 7, which is about the induction machine. So let's start. At what speed will a 12 pole 60 Hz induction motor operate if the slip is 6%? So in this question we know the number of poles, the frequency and the slip. If you know the number of poles and the frequency, you can calculate the synchronous speed. So the synchronous speed is equal to 120 times the frequency over the number of poles. So we can calculate the synchronous speed if we know the number of poles and the frequency. And if we know the synchronous speed and the slip, we can calculate the speed, the mechanical speed of the motor. So the mechanical speed of the motor will be 1 minus s times ns, which is synchronous speed. So we know the slip, we know the synchronous speed, so we can easily calculate the motor speed or the mechanical speed. In question 2, a 60 Hz 8-pole induction motor runs at 860 RPM at full load. Determine first the synchronous speed, B the frequency of the rotor currents, and C the rotor speed relative to the revolving field. So first the synchronous speed. Again, the synchronous speed could be calculated if we know the number of poles and the frequency. So we know the number of poles and the frequency, so we can calculate the synchronous speed. Now if we want to calculate the frequency of the rotor current, which is the frequency of the rotor, we should multiply the synchronous, the frequency of the stator times the slip. So we know the frequency of the stator, which is given as 60 Hz, but we need to calculate the slip. Now we know the synchronous speed, we know the motor speed, so we can calculate the slip, which is equal to ns minus nm over ns. So we can calculate the slip, and we can multiply the slip times the frequency of the stator to calculate the frequency of the rotor, which is the frequency of the rotor currents. Finally, for part C, we need to calculate the rotor speed relative to the revolving field. Now for the revolving field, the field is rotating at speed equal to ns, and the rotor itself rotates at the motor speed, which is nm. So the relative speed will be ns minus nm, which will be 40 rpm. So that was the answer of this question. For the third question, if the EMF in the stator of a 6-pole induction motor has a frequency of 60 Hz and that in the rotor of 2 Hz, at what speed is the motor running and what is the slip? So we know the frequency of the rotor and the frequency of the stator, so we can calculate the slip, which is the ratio of the frequency of the rotor to the frequency of the stator. After we calculated the slip, we can calculate the mechanical or the motor speed if we know the synchronous speed. Of course we know the synchronous speed because we know the number of poles and the frequency, so we can calculate the synchronous speed, and then we can calculate the motor or the mechanical speed. In question 4, a 3-phase 20 horsepower 220 voltage 60 Hz 6-pole Y-connected squirrel cage induction motor has the following parameters per phase in stator terms. So we know R1, R2, X1 and X2, XM, and the rotational losses, and also the slip. And it's required to calculate the line current and power factor, the horsepower output and shaft torque, and finally the efficiency. So this is a very important question. In this question we have an induction motor, and the voltage here is the terminal voltage or the supply voltage for this motor. So from the equivalent circuit, we can calculate the equivalent impedance. So we will have impedance for the primary side, impedance for the secondary, and the XM, which is the magnetization reactance between X1 and between Z1 and Z2. So Z2 is equal to R2 over S plus JX2, and which is parallel to GXM. So this part here, to calculate GXM parallel to Z2, then this is added to the primary impedance. So we have the equivalent impedance here. So the machine now is, we calculated the equivalent impedance for this machine. And we know the input voltage, which is a supply voltage. So V1 over this impedance is equal to the input current. And the power factor in this case will be the angle of the voltage, which is assumed to be 0, minus this angle of the current. So cosine this difference is equal to the power factor. Don't forget to divide this voltage over root 3, because here we have Y connected machine. So this for the first part. For the second part, we wanted to calculate the horsepower output and shaft torque. So we can calculate the air gap power. The air gap power is the input power minus the stator copper loss. So the input power is equal to V line, which is given, I1, which is calculated in the first part, and times the power factor, which is already calculated in the first part, times root 3. So this is to calculate the input power. For the stator copper loss, I input square times R1 times 3, because we have 3 phases. So this is the total stator copper loss. So the input power minus the stator copper loss is equal to the air gap power. And if we know the air gap power, we can convert this to the converted power by multiplying the air gap times 1 minus S. So 1 minus S times the air gap power is equal to the converted power, or the developed power. Now this is the developed power, and as you know, the developed power minus the losses is equal to the output power. So we can calculate the output power because the losses is given. And in order to calculate the torque, we need to calculate omega. And in order to calculate omega, we need to calculate Nm, which is a motor speed. And in order to calculate the motor speed, we need to calculate the synchronous speed. So we will calculate first the synchronous speed, then we can calculate the motor speed. After that, we can calculate omega in order to calculate the output torque, which is equal to the output power over omega. If the question is about the developed torque, it will be the developed power over omega. So don't forget that. This is very important. In the final part, the efficiency, and this we can calculate the efficiency very easily here because we know the input power and the output power. So we can just divide the output power over the input power to calculate the efficiency of this machine. In question 5, a 3-phase induction motor is supplying 100 horsepower to a coupled mechanical load. At this point of operation, the rotational losses are given, the total core losses are given, the stator coil copper losses are given, and the slab is given. So we know the losses of the stator, the losses in the core, the rotational losses, and the output power, and the slab. And we need to calculate the efficiency. And for part B, we need to calculate the rotor copper loss. So let's start. So in order to calculate the efficiency, we need the output power and the input power. We have the output power. So we should go backward in order to calculate the input power. So we know the output power, it's given. So the output power plus the losses will be equal to the converted power or the developed power. So this is the first step. We can calculate the converted power. And because we know the slab, we can calculate the air gap power. So the air gap power will be the converted power or the developed power over 1 minus S. So we can calculate the air gap power. And if we know the air gap power, we can calculate the input power, because the input power is equal to the air gap power plus the stator copper loss. So the stator copper loss and the core loss, of course, plus the air gap power is equal to the input power. So now we know the input power and the output power, so we can calculate the efficiency. For part B, which is very tricky here, to calculate the rotor copper loss. In order to calculate the rotor copper loss, there is a relation between the rotor copper loss and the air gap power. And also you can calculate that because we know the converted power and the air gap power. So we can subtract the converted power from the air gap power in order to calculate the rotor copper loss. In question 6, a 3-phase 8-pole 50 horsepower, 460 voltage, 60 Hz, 865 RPM induction motor is operating at rated conditions and has this input power, this input current, and it's known that R1, which is a stator resistance, is given, and the rotational losses at rated speed are given. It's required to calculate the full load power factor, the full load efficiency, total rotor copper losses, and total core losses. So for the first part, we need to calculate the power factor. This is very straightforward because we know the input power, the input current, and the input voltage. So we can divide the input power over the input voltage and the input current to calculate the power factor. Don't forget root 3 because here we have a 3-phase, or 3 if you are going to use phase values. For part B, the efficiency, we know the output power and the input power, because here he's asking about the full load. So the full load means that this will be our output power, which is 50 times 746. Input power is given, so we can calculate the efficiency. Also, this is very straightforward. Now we need to calculate the rotor coil losses. So now, in order to calculate the rotor coil loss, we need to calculate the converted power and the air gap power. So in order to calculate the converted power, we have the output power and we have the losses, so we can calculate this part. We can calculate the air gap power, which is the converted or the developed power over 1 minus S. And we can subtract this power from this one to calculate the rotor copper loss. Or, as I told you in the previous question, there is a relation to calculate the rotor copper loss, which is equal to the slip times the air gap power. So you can use this to calculate the rotor copper loss. For the total core losses, so the core loss is equal to the input power minus the stator copper loss minus the air gap power. So we should calculate the stator copper loss here. We have the input current, we have the resistance, so we can calculate the stator copper loss, and after that we can calculate the core losses. So that's all for this problem set and for this term, of course. If you have any question, please email me or book an appointment in the one-to-one session, and I will be happy to answer your question. Thank you.